This section will be an introduction to polar coordinates. Now, polar coordinates are another way to describe a location in 2 dimensions, and it's just more convenient than Cartesian coordinates or rectangular coordinates for certain applications. So the way we convert between the 2 systems is shown with this sketch over here. So notice that this is a radius of r, so we're not on a unit circle now, we're just on any location here. This can be any distance you want. So this point is given by x comma y, so x is the distance to the right, y is the distance up. It's also given by r comma theta, where r is the direct distance and theta is the angle that's made with the positive x-axis. So this is also called the polar axis, and this is the angle going up. So besides being called the origin for Cartesian coordinates, for polar coordinates, this is called the pole. And so given the fact that this point is x comma y and r comma theta, and what these each mean, we can convert as follows. If we want to go from rectangular to polar, r is equal to the square root of x squared plus y squared, of course, by the Pythagorean theorem. To get theta, notice that tan theta is y over x, so therefore theta will be the inverse tan of y over x, with one caveat. Sometimes you have to add 180 degrees or pi, because inverse tan only evaluates in the first and fourth quadrants. So if you're in the second or third, you'll have to take your answer from inverse tan y over x and add pi. How would you know if you're in these quadrants? Well, simply if x is less than 0, you know in one of these 2 quadrants, so you would have to add that on. Going the other direction, if you're given r and theta, noting that cosine theta is adjacent over hypotenuse and sine theta is opposite over hypotenuse, well, that's simply x is r cosine theta and y is r sine theta. And if we're on a unit circle, r would be 1, and we see our familiar cosine theta comma sine theta for our location. So that's the conversions between the 2 types. So now let's take a look at some of the pictures, vocabulary examples, and so forth. So this is what I mentioned a moment ago, how you've got theta is the angle from the polar axis, r is the directed distance. Plotting some points, 2 comma pi over 3, you go at an angle of pi over 3 and you go a distance 2 to get to this point. 3 negative pi over 6, negative pi over 6, angle this way, you go at a distance 3. 3 comma 11 pi over 6, 11 pi over 6 is all the way around here, you go a distance of 3. Notice these are the same place. Now in Cartesian coordinates, there's only one set of coordinates to define a single point. But in polar coordinates, you can use an infinite number of coordinates to define a single point because of the periodicity of the circle. Now, in addition to that, here's the multiple representation of points. There's other ways to represent points. We've got this point 3 comma negative 3 pi over 4. Negative 3 pi over 4 is this angle. You go out a distance 3, which is the same as 3 comma 5 pi over 4, because 5 pi over 4 is this angle. Go at 3. We can also use negative r values. Negative 7 pi over 4 would be going this direction back to here, but since you're going negative 3, instead of going that direction, you go the exact opposite way, and of course you end up where we want to be. So multiple representation of points. This is the coordinate conversions I mentioned already. Here we see them. So examples of coordinate conversion. We have 2 comma pi. If you want to get x, it's 2 cosine pi. Y is 2 sine pi, and you end up with negative 2, 0, which makes sense because an angle of pi is directly to the left. If you've gone a distance 2, you're at negative 2. It's an angle pi. You haven't gone up or down at all, so that's a height of 0 for y. Rad 3 pi over 6. X is rad 3 cosine pi over 6. Y is rad 3 sine pi over 6, and we get these values as shown. Here's rectangular to polar. We've got the point negative 1, 1 over here. It's a good idea to think about graphically what's going on, especially in this situation where you're looking for angles. So tan theta is negative 1. If you did inverse tan, you would get actually negative pi over 4, but you need to realize this is 3 pi over 4 because, of course, we're in quadrant 2. So visualize what's going on here. And then for 0 comma 2, 0 comma 2 is up over here. You use the conversions if you want, but it's also just good to realize that this is an angle of pi over 2. It's straight up, and you haven't deviated left or right at all, so clearly you've gone a distance of 2, so it's 2 comma pi over 2. We can also convert equations. So using our same coordinate conversions, we can convert equations. R equals 2 is saying all points 2 away from the pole, and so hopefully you understand that that would be a circle, because you can go in any angle you want. And if you convert that, you see that it does give you the equation of a circle. Since r is the square root of x squared plus y squared, we know that r squared is x squared plus y squared, so we get x squared plus y squared equals 2 squared, x squared plus y squared equals 4, which is, of course, the equation of that circle. Theta equals pi over 3 defines the angle, but not the distance you're going. So as long as you're anywhere on this angle, positive r or negative, satisfies the equation. And so using our coordinate conversions, that is tan theta is y over x, we just end up with y equals rad 3x, y-intercept of 0, goes through the pole, the origin, right, and has the slope of rad 3. Lastly, r equals secant theta. Well, we can rewrite this as r cosine theta equals 1, basically by multiplying both sides by cosine. R cosine theta is the same thing as x, so we get x equals 1, which is this vertical line. So now on to a little bit of graphing. Here's a polar template. So we have all of the angles, reference angles shown. We've got our 30, actually here's our 15, 30, 45, 60, 75, and 90. So really what we really need to focus on is the zeros, the multiples of 30, and the multiples of 45. So if we're doing r equals 4 cosine theta, we just plug in values for theta to get values of r. So even though it's r comma theta, we don't plug in r to get theta, we plug in theta to get r. So if you plug in 0, cosine of 0 is 1, 4 times 1 is 4, pi over 6, cosine of pi over 6 is rad 3 over 2, times 4 is about 3.7. And so I plot these points. So this one is, for instance, is an angle pi over 6 going at 123.6. This is an angle of pi over 4 going out 2.8, and so on. And note that when we get back to an angle of pi over 2, our distance is 0. So we're at the pole. So no matter what angle you go at, if your r value is 0, you're at the pole. Now what we see when we get to 2 pi over 3, which would be this angle over here, is that our r value is negative 2. And so we come back actually the opposite direction, 1, 2. And what will happen is we'll end up getting a circle here, which will have a radius of 2, and it'll be centered at 2, 0. And actually, we get the entire circle simply by going from 0 to pi, because once you get down to 7 pi over 6, you're just going to repeat the circle again. You'd actually see redrawing the circle. So sometimes you need a full complement 0 to 2 pi or more. Sometimes you need less, and this is a case where you need less. Now it turns out that you can also use your calculator to do some coordinate conversions, so I'll show you a little bit of that. So let's say we want to convert from, let's try this, we do second angle, and let's go over here. And if we want to go from rectangular to polar, let's pick number 5, so that's rectangular to your polar r value. So I need rectangular, so for instance, how about 3, 4? And so this should give me 5, and there you go, it does. Now if we do, say, second angle, and we want to get polar to our x value. So actually I did wrong thing. So second angle, polar to our x value is number 7 here. So we need a polar coordinate, so we'll say negative 2 comma pi divided by 3. And this will give us the x value, and there it is, it's negative 1, turns out. So you can use your calculator to do some of these conversions too, but the main thing is to see what's going on graphically. A few sample problems. This is a problem where it's just showing multiple representation of points, negative 6 and 0 radians. Well, 0 radians is over here. Negative 6, though, is going to put you this direction. So this would be at a distance of negative 6. So it's this point here. That's the same as 6, 180. You go 180 degrees, you go a distance of 6. 6, 180, of course, is the same as 6, 540, because 540 and 180 are coterminal. Or you can also do negative 6, 0 degrees. 0 degrees and 0 radians turns out to be the same spot. So negative 6 from either place puts you on the left. This is an equation conversion. We have a rectangular equation. We want to convert it to polar. So x squared plus y squared, first of all, is r squared. So we've got r squared squared minus 9. Then x squared is the same as r cosine theta squared, because x is r cosine theta. Likewise, y is r sine theta. So we have r sine theta squared equals 0. We'll clean it up a little. This is r to the 4th minus 9. I'll factor out the r squareds from these two, and I'm left inside with cosine squared theta minus sine squared theta. Now I'll divide off an r squared from both of these pieces. I can add this to the other side, because usually you try to solve for r or r squared in the same way that you try to solve for y, for rectangular. and I've got r squared is 9 cosine squared theta minus sine squared theta. Using your double angle formula, you end up with r squared is equal to 9 cosine 2 theta. And then this is one more going rectangular to polar. So first I'll add the 2 to the right. X is the same as r cosine theta. Y is the same as r sine theta. I factor out an r, and then I divide both sides to get r by itself. And so this is a somewhat more complicated version, of course, of this original line that does not go through the origin, as we saw examples of ones going through the origin before.